Welcome to myprojectbazaar.com. Let me discuss about the project Electrocardiogram signal modeling with adaptive parameter estimation using sequential Bayesian methods. Let me discuss about the abstract of the project. In this method, the algorithm used is support vector machine-based methods to effectively model and adaptively select parameters of ECG signals. In this method, first focused on the adaptive framework-based sequential support vector machine is proposed to select the best cardiac parameter and then to eliminate the error or by reduction of error. We then present ECG modeling techniques using the interacting multiple model methods combined with simultaneous model selections. Both these methods can adaptively choose between different representation to model various ECG beat morphologies without requiring prior ECG information. The proposed system processes are done by real ECG data under the SVM classification. In this proposed system of ECG signal modeling, we first give importance to adaptive framework-based SVM classification method is used to select the best cardiac parameter. The further process is eliminating the fault signals or reduction of error signals. ECG modeling techniques method is using the interacting multiple models IMM methods. Compare with simultaneous model selections. Above, the two methods can adaptively select between different representation to model various ECG beat morphologies without requiring prior ECG information. The processes are done by real ECG data under the support vector machine classification. The multi-layer perception is a feed-forward artificial neural network model and that maps sets of input data onto a set of appropriate outputs. The MLP consists of multiple layers of nodes in a directed graph, with each layer fully connected to the next one. Except for the input nodes, each node is a neuron with a nonlinear activation function. MLP utilizes a supervised learning technique called backpropagation for training the new network. MLP is a modification of the standard linear perception and can distinguish data that are not linearly separable. Let me discuss about the flow diagram for our process. First, capture the ECG signal from the dataset folder. Here, load the ECG signal from ASCII format to array for the display. Then we have to pre-process the ECG signal for the removal of unwanted noise and baseline wander from it. Perform zero-phase digital filtering by processing the input ECG data in both the forward and reverse direction. After filtering the ECG signal in the forward direction, it reverses the filtered sequence and runs it back through the filter. The resulting sequence has precisely zero-phase distortion and double the filter order. Pre-processed signal will also be displayed and its corresponding quality measures were calculated. Here the entire data set, that is entire data set ECG signal are processed as a training phase, and in the feature extraction phase, wavelet based features will be extracted from the ECG signal. Different abnormalities result in different changes in the coefficients. Orthogonal dyadic discrete wavelets are associated with scaling functions. The scaling functions can be convolved with the signal to produce approximation efficient. In the discrete wavelet transform, the wavelet transform has gained widespread acceptance in signal processing and image analysis. Because of their inherent multi-resolution nature, coding schemes are specially suitable for application where scalability and tolerable degradation are important. The wavelet transform is computed separately for different segments of the time domain signal at different frequencies. Multi-resolution analysis analyzes the ECG signal at different frequencies, giving different resolutions. Next, in the feature selection phase, automatic feature selection is an optimization technique that, given a set of features, attempts to select a subset of size that leads to the maximization of some criterion functions. Feature selection algorithms are important to recognition and classification systems because if a feature space with a large dimension is used, the performance of the classifier will decrease with respect to execution time and to recognition rate. The execution time increases the number of features because of the measurement cost. The recognition rate can decrease because of the redundant features and the fact that a small number of features can alleviate the cause of dimensionality when the training sample set is limited. Next, in the abnormality detection stage, the cardiovascular abnormalities detection is based on the heart rate, that is HR calculation. HR is calculated from the extracted features of ECG signal by finding the inverse of RR interval, which is the time differences between two consecutive R peaks present in every QRS complex. Finally, we obtain the prediction result. With the prediction result, we evaluate the performance for our systems. The episode direction performance is measured in terms of sensitivity and positive predictive accuracy. The sensitivity parameter measures the ability to detect symmetric episode, whereas positive predictive accuracy provides the estimation likelihood that the detected episode is a true ischemic episode. Let me discuss about the running procedure for our process. Select the main.temp file in the current folder, right-click that file and run for executing this process. This is the main window of the analysis the ECG signal using feature selection. By pressing the input signal button, we can browse the input signal from the dataset folder. Here, select any one signal from the dataset folder. Here I display the input signal in the axis 1 plot. By pressing the pre-processing button, we perform the filtering operation. This is the moving average filter result and this is the low pass butterworth filter result. I display in the axis 2 plot. By pressing the feature button, we can perform the feature extraction process. This is the feature extraction window. By pressing the morphological parameter button, we can perform the morphological operation. Here I display the morphological parameter value in the table format. And by pressing the spectral parameter button, we can perform the spectral parameter calculations. Here I display the spectral parameter value in the table 2. And by pressing the complexity parameter button, perform the complexity parameter operations. Here I display the complexity parameter in table 3. By pressing the next button, we come back to the main window. And by pressing the peak signal button, we estimate the peak signal value. This is the filtered and smooth processed signal for every R wave, S wave and T wave representation. This is the raw ECG signal and this is the heart rate for our current ECG signal. Here I display heart rate as 65. By pressing the final analysis button, we perform the SVM classifier result. And here we obtain the result as tachycardia. That is, this arrhythmia ECG signal represents tachycardia arrhythmia. And this is the abnormal cases of ECG signal. And this is the performance measures for accuracy, sensitivity and specificity of our SVM classifier. The proposed innovation approaches for automatic classification and detection of various arrhythmia diseases by using currently emerging classifier techniques such as SVM classifier. Thank you.